Hello there, and welcome. I'm so glad you found your way here tonight. Maybe you've had a long day filled with numbers and equations, or perhaps you're simply the kind of person who finds comfort in the vast mathematical patterns that govern our universe. Either way, you're in exactly the right place. Tonight's journey is designed for rest, for wonder, and for letting your mind drift through the gentle currents of cosmic mathematics. You have nothing to do but relax. Let your breathing slow, your muscles soften, and your thoughts settle like dust particles finding their place in the stillness of space. Because tonight, we're not just exploring mathematics, we're following the ancient path of a wanderer, a visitor from another star system, a comet that has traveled for billions upon billions of years through the darkness between the stars. This visitor has a name, 3I Atlas, the third interstellar object ever discovered passing through our solar system, and embedded in its journey are mathematical stories so profound, so ancient, that they predate not just human civilization, not just the dinosaurs, but perhaps even our own sun and earth. The numbers we'll explore tonight stretch across timescales that challenge comprehension, distances that dwarf our everyday experience, and velocities that approach the limits of what gravity will allow. Some of what you hear may surprise you. The mathematics might spark curiosity even as you drift towards sleep, and that's perfectly fine. Let the numbers wash over you like gentle waves. Let the equations become a kind of meditation, a rhythm, a pattern that guides you deeper into rest. Before we begin our mathematical journey through time and space, if these explorations help you unwind, if they give you a peaceful way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time, one mathematical story at a time. Now let's begin with a number, a simple number that will grow into something extraordinary. The number is 3. The letter is I. Together, 3I, the third interstellar object. On July 1st, 2025, at a telescope facility in Chile's high desert, where the Andes Mountains meet the Atacama, where the air is thin and the skies are among the clearest on Earth, an automated survey system detected something unusual against the backdrop of distant stars. The Asteroid Terrestrial Impact Last Alert System, known by its acronym ATLAS, had been methodically scanning the heavens, night after night, looking for objects that might pose a threat to our planet. On this particular night, as the telescope's camera captured frame after frame of the star-filled sky, an algorithm noticed something peculiar, a faint smudge of light, a point source that wasn't in the stellar catalogs, something moving. The initial observation was recorded at Observatory Code T05, the Atlas facility in Rio Hurtado, Chile. The object appeared at an apparent magnitude of approximately 20, meaning it was more than 1,000,000 times fainter than the faintest stars visible to the human eye on a dark night. Only sensitive cameras attached to powerful telescopes could detect it. But the automated system flagged it immediately. Something was there, something moving against the background of the cosmos. At first, there was uncertainty. The nature of the object wasn't immediately clear. Was this an asteroid, a rocky body that had wandered in from the asteroid belt between Mars and Jupiter? Was it a comet, an icy visitor from the outer reaches of our solar system? The object was approximately 670 million kilometers from the Sun, positioned within the orbital path of Jupiter. At this distance, many objects could be found, remnants of the solar system's formation scattered across the vast spaces between the planets. Within hours of the initial detection, the discovery was reported to the Minor Planet Center, the international clearinghouse for observations of asteroids, comets, and other small bodies in our solar system. The alert went out to observatories around the world. Professional astronomers and amateur observers alike began turning their instruments toward the coordinates, hoping to capture additional observations, to refine the orbit, to understand what this object might be. For days, telescopes across the globe tracked this mysterious visitor. Each observation added a data point, a precise measurement of position and time. The Deep Random Survey Telescope in Chile obtained images on July 2nd. The Lowell Discovery Telescope in Arizona captured it. The Canada-France-Hawaii Telescope atop Mauna Kea in Hawaii added its observations. With each passing hour, with each new measurement, the mathematical picture grew clearer. And then astronomers began searching through older images, looking back through archived observations to see if this object had been photographed before but not recognized. This practice, called pre-discovery recovery, often extends the baseline of observations dramatically, allowing for much more precise orbital calculations. They found it. The Zwicky Transient Facility at Palomar Observatory in California had captured images of the object on June 28th and 29th, several days before the official discovery. They found it again in images from June 14th through 21st. More ATLAS observations turned up from June 5th through 25th. With each pre-discovery image, the orbital arc grew longer, the mathematical constraints tighter. Amateur astronomer Sam Dean noted something interesting about these pre-discovery observations. The object had been passing in front of the galactic center, that dense concentration of stars toward Sagittarius, where the Milky Way's heart lies hidden behind veils of dust. Against this crowded stellar background, the faint comet would have been difficult to discern, easy to overlook amid millions of stars. Only as it moved away from this dense region did the automated systems pick it out clearly. The initial observations showed no obvious cometary features. The object appeared point-like, star-like, similar to an asteroid, but on July 2nd, multiple observatories began reporting something different. The Deep Random Survey in Chile noted a marginal coma, a faint haze surrounding the central point. The Lowell Discovery Telescope confirmed it. The Canada-France-Hawaii Telescope reported a potential tail-like elongation, stretching about 3 arcseconds, a tiny apparent length that suggested material streaming away from the nucleus. These observations were crucial. They indicated that the object was releasing gas and dust, that it was being heated and activated by the increasingly intense sunlight as it fell deeper into the inner solar system. This was not an inert rock. This was a comet, an icy body responding to the sun's warming radiation. On July 2nd, the Minor Planet Center made its official announcement. They designated the object 3I Atlas, a name dense with meaning. The I stands for interstellar, indicating that this object came from beyond our solar system. The 3 signifies that this is the third such interstellar object officially confirmed. The first was 1I, Oumuamua, discovered in October 2017 an elongated object that showed no cometary activity. The second was 2I Borisov, discovered in August 2019, a comet that behaved much like comets from our own solar system. And now, 3I Tau Atlas, the third visitor from another stellar system to pass through our neighborhood. The MPC also gave it the non-periodic comet designation CES 2025 N1 Atlas, following the traditional naming convention for comets. By the time this designation was assigned, 122 observations of the comet had been collected from 31 different observatories spread across the globe. Professional and amateur astronomers, large research telescopes, and backyard instruments, all contributing to humanity's understanding of this ancient wanderer. Additional confirmations came quickly. David Jewett and Jane Liu, renowned astronomers who had made fundamental contributions to our understanding of the outer solar system, observed the comet using the Nordic Optical Telescope. On July 2nd, they confirmed that 3I Atlas was clearly active, showing a diffuse appearance characteristic of comets releasing gas and dust. And then the mathematics began to tell an extraordinary story, a story written in orbital elements, in calculations of trajectory and velocity, in numbers that described not just where this object was, but where it had been and where it was going. The evidence was written in numbers, in velocity measurements that exceeded the escape speed from the sun by comfortable margins, in a trajectory that curved but never closed, a path that entered our solar system from the depths of space and would return there again, in the shape of its orbit expressed through a mathematical parameter called eccentricity. Pre-discovery images were found, stretching back to June 14th, giving astronomers nearly 2 months of observations to work with. Observations from multiple telescopes around the world confirmed what the initial calculations suggested. This object wasn't just passing through our solar system. It hadn't originated in the Oort cloud, that vast spherical shell of icy bodies surrounding our sun at distances up to 100,000 astronomical units. It hadn't been kicked out of the Kuiper belt beyond Neptune. It had come from somewhere else entirely, from the vast spaces between the stars, from another stellar system, perhaps one that formed billions of years, inches before our own sun, perhaps one that lived and died long ago, scattering its planetary children into the cosmic void. The mathematics made this clear. The orbital calculations, performed independently by researchers around the world, all converged on the same conclusion. The numbers didn't lie. They couldn't be made to fit a solar system origin, no matter how the calculations were adjusted or refined. Let me share with you the mathematics that revealed this truth, and let those numbers become a gentle rhythm as we explore together. Let the equations unfold slowly, naturally, like a story told by the universe itself through the language of mathematics. To understand what makes 3I Atlas so remarkable, we must first understand a fundamental concept in orbital mechanics: escape velocity. And to understand escape velocity, we need to think carefully about the invisible bonds that hold objects in orbit around the sun, bonds woven from gravity itself, bonds that can be measured and calculated with precision. Imagine standing on Earth's surface and throwing a ball upward into the sky. You release it, and it rises, carried by the momentum you've given it. But even as it climbs, Earth's gravity pulls it back down. The ball slows in its ascent, reaching a maximum height, then falls back to your hand. No matter how hard you throw it, the ball comes back down. Gravity's embrace is inescapable for everyday throws. Now imagine throwing harder, imparting more and more speed to the ball at the moment of release. The ball rises higher with each throw. Throw it fast enough, and it might rise kilometers into the atmosphere. But still, eventually, gravity wins. The ball reaches its apex and descends. But there's a threshold, a specific velocity. If you could somehow throw the ball at exactly this speed, something remarkable would happen. The ball would keep rising forever. It would slow down continuously as Earth's gravity pulled at it, but it would never quite stop. At infinite distance, it would reach zero velocity. This threshold speed is called escape velocity. For Earth, that number is approximately 11.186 kilometers per second. Let's express this in more familiar units to appreciate its magnitude. 11.186 kilometers per second equals approximately 40,270 kilometers per hour. In miles per hour, that's about 25,000 miles per hour, or to be more precise, 24,837 miles per hour. This is extraordinarily fast. A commercial jet aircraft might fly at 900 kilometers per hour. Escape velocity from Earth's surface is about 45 times faster than a jet. A bullet from a high-powered rifle might travel at 1 kilometer per second. Escape velocity is more than 11 times faster than this bullet. To put it another way, at escape velocity, you could travel from New York to Los Angeles, a distance of approximately 4,000 kilometers, in less than 6 minutes. You could circumnavigate the Earth's equator, a journey of 40,000 kilometers, in about 54 minutes. But Earth orbits the Sun, and the Sun has its own gravitational field, vastly more powerful than Earth's. From our perspective on Earth, we're already moving at about 29.78 kilometers per second in our orbit around the Sun. But to truly escape the solar system, to break free from the Sun's gravity, requires additional speed. The escape velocity from any gravitating body can be calculated using a beautiful and simple equation. V equals the square root of 2 times g times m divided by ar, where v is the escape velocity, g is the universal gravitational constant, with a value of 6.674 times 10 to the negative 11th cubic meters per kilogram per second squared. M is the mass of the gravitating body, and r is the distance from the center of that body. For the Sun, with a mass of 1.989 times 10 to the 30 kilograms, at Earth's orbital distance of 1 astronomical unit, which equals 1.496 times 10 to the 11 meters, we can calculate V equals the square root of 2 times 6.674 times 10 to negative 11 times 1.989 times 10 to 30 divided by 1.496 times 10 to 11. Simplifying the numbers inside the square root, 2 times 6.67, 4 times 10 to negative 11 times, 1.989 times 10 to 30 equals approximately 2.654 times 10 to the 20, divided by 1.496 times 10 to 11 equals approximately 1.774 times 10 to the 9. Taking the square root, approximately 42.1 kilometers per second. This is the escape velocity from the Sun at Earth's orbital distance. If you're sitting at Earth's orbital radius, You need to be moving at 42.1 kilometers per second or faster to escape the solar system entirely. This is about 1.4 times faster than Earth's orbital velocity of 29.78 kilometers per second. Now here's where 3I Atlas reveals its nature through mathematics. When the comet was first discovered in early July 2025, still far from the Sun at approximately 670 million kilometers, it was already moving at a velocity of approximately 221,000 kilometers per hour relative to the Sun. Let's convert this to kilometers per second to compare with escape velocity. 221,000 kilometers per hour divided by 3,600 seconds per hour equals approximately 61.4 kilometers per second. At the comet's distance from the Sun at the time of discovery, approximately 4.5 astronomical units, we can calculate the local escape velocity. V equals square root of 2 times g times m divided by r, where r is now 4.5 times 1.496 times 10 to 11 meters, which equals 6.73, 2 times 10 to 11 meters. U equals square root of 2 times 6.674 times 10 to negative 11 times 1.989 times 10 to 30, divided by 6.732 times 10 to 11. This equals square root of 3.948 times 10 to 8, which equals approximately 19.87 kilometers per second. The comet was moving at 61.4 kilometers per second. The local escape velocity was only 19.87 kilometers per second. The comet's velocity exceeded escape velocity by a factor of more than 3. This object was not bound to the Sun. It had far more than enough energy to escape our solar system. As 3I Atlas fell deeper into the inner solar system, approaching the Sun's gravity accelerated it, just as a ball you throw upward would accelerate as it falls back down. Following its hyperbolic trajectory, the comet's speed increased continuously. At perihelion, the point of closest approach to the Sun, on October 29th, 2025, the comet reached its maximum velocity relative to our star, approximately 246,000 kilometers per hour. Converting to kilometers per second, approximately 68.3 kilometers per second. At its perihelion distance of 1.36 astronomical units from the Sun, or approximately 2.03 times 10 to 11 meters, the local escape velocity would be v equals square root of 2 times 6.674 times 10 to negative 11 times 1.989 times 10 to 30 divided by 2.03 times 10 to 11. This equals square root of 1.308 times 10 to 9, which equals approximately 36.2 kilometers per second. The comet's velocity of 68.3 kilometers per second exceeded this local escape velocity by a factor of about 1.89, still comfortably above the threshold needed to escape. These numbers tell an unambiguous story. At every point in its trajectory through our solar system, 3I Atlas moved faster than escape velocity. The Sun's gravity bent its path, certainly, pulling it into a curve as it swooped through the inner solar system. But the Sun couldn't capture it. The comet had too much energy, too much velocity. It was just passing through, like a traveler crossing through a city on a journey that began long before and will continue long after. But how do we express this mathematically in a more formal way? How do we capture in equations the difference between an object that belongs to our solar system, bound forever to orbit the sun, and one that merely visits, destined to return to the interstellar void? The answer lies in a dimensionless number, a pure ratio, called orbital eccentricity, and it's in this number that the true nature of 3I Atlas becomes mathematically explicit and undeniable. Every orbit around a gravitating body follows the path of what mathematicians call a conic section. And these geometric shapes have fascinated mathematicians and astronomers for millennia, and they emerge naturally from the laws of gravity and motion that govern our universe. The conic sections are the shapes you get when you slice through a double cone, two identical cones placed tip to tip at different angles with a plane. Slice the cone parallel to its base, and you get a circle. Tilt the plane slightly, and the circle elongates into an ellipse. Tilt it further until it's parallel to the side of the cone, and you get a parabola, an open curve that extends to infinity. Tilt it even more, cutting through both cones, and you get a hyperbola, a curve with two separate branches. These mathematical shapes, studied by the ancient Greeks, turn out to describe all possible orbits in a gravitational field. It's a beautiful example of how abstract geometry connects to physical reality, how the mathematics discovered by scholars contemplating pure form reveals itself in the motion of objects through space. For objects gravitationally bound to the sun, their orbits follow ellipses. An ellipse is a closed curve, a stretched circle defined by two focal points. For a planetary orbit, the sun sits at one focus and the other focus is empty, a mathematical point with no physical significance. The shape of the ellipse is characterized by its eccentricity, denoted by the letter E, a dimensionless number that describes how stretched or elongated the ellipse is. A perfect circle is actually a special case of an ellipse where the two foci coincide at the center. For a circle, the eccentricity equals 0. As you stretch the ellipse, pulling the foci apart, the eccentricity increases. A slightly elongated ellipse might have an eccentricity of 0.1 or 0.2. A very stretched ellipse, long and narrow, might have an eccentricity of 0.8 or 0.9. But for any closed ellipse, for any bound orbit, the eccentricity is always greater than 0, but less than 1. Let's consider some examples from our solar system to build intuition for what these numbers mean. Earth's orbit has an eccentricity of approximately 0.01671. This is very close to 0, meaning Earth's orbit is very nearly circular. The difference between Earth's closest approach to the Sun, called perihelion, and its farthest distance, called aphelion, is only about 5 million kilometers. Perihelion distance is approximately 147.1 million kilometers. Aphelion distance is approximately 152.1 million kilometers. The average is 149.6 million kilometers, which is essentially 1 astronomical unit. We can verify the eccentricity using the relationship. E equals R aphelion minus R perihelion divided by R aphelion plus R perihelion. For Earth, A equals 152.1 minus 147.1 divided by 152.1 plus 147.1 equals 5 divided by 299.2 equals approximately 0.0167. This matches the known value. Earth's orbit is indeed very nearly circular, Mars has a more eccentric orbit. Its eccentricity is approximately 0.0934. This means Mars's distance from the Sun varies much more than Earth's. At perihelion, Mars comes within approximately 206.6 million kilometers of the Sun. At aphelion, it recedes to approximately 249.2 million kilometers. That's a difference of about 42.6 million kilometers, much larger than Earth's variation. Some comets in our solar system have even more eccentric elliptical orbits. Halley's Comet, perhaps the most famous periodic comet, has an eccentricity of 0.967, very close to 1. Its perihelion distance is only 0.586 AU, bringing it closer to the Sun than Venus. But its aphelion distance is approximately 35.08 AU, well beyond the orbit of Neptune. The comet swings from the inner solar system out past the giant planets and back again on its 76-year journey around the Sun. As the eccentricity of an ellipse approaches 1, the ellipse becomes more and more elongated, stretching toward a parabola. At exactly e equals 1, mathematically speaking, the curve transitions from closed to open. This is the theoretical boundary between bound and unbound motion. An eccentricity of exactly 1 represents a parabolic trajectory. An object on a parabolic orbit has precisely the amount of energy needed to escape to infinity, where it would arrive with exactly 0 velocity. It's a perfect balance, a knife edge between bound and unbound. In practice, truly parabolic orbits are rare. Most objects either have a bit less energy, making them elliptical and bound, or a bit more energy, making them hyperbolic and unbound. And what happens when the eccentricity exceeds 1? Then we enter the realm of hyperbolic trajectories. These are open curves that never close, paths that extend to infinity in both directions. An object on a hyperbolic trajectory passes by the Sun once and never returns. It has excess energy, more than enough to escape. Even at infinite distance from the Sun, it still retains some velocity, called the hyperbolic excess velocity, or velocity at infinity. The mathematics of hyperbolic orbits is elegant. For any orbit, the eccentricity can be calculated from the orbital energy and angular momentum using E equals square root of 1 plus 2 times epsilon times hh squared divided by mu squared, where epsilon is the specific orbital energy per unit mass, h is the specific angular momentum per unit mass, and mu is the gravitational parameter of the central body, which for the Sun equals g times m, equals approximately 1.327 times 10 to the 20 cubic meters per second squared. The specific orbital energy epsilon for a hyperbolic orbit is positive. This is the key signature. For elliptical orbits, the energy is negative, meaning the object is trapped in the gravitational well. For parabolic orbits, the energy is exactly 0. For hyperbolic orbits, the energy is positive, meaning the object has more than enough kinetic energy to escape the gravitational well entirely. We can relate this energy to the velocity at infinity, the speed the object retains even after escaping to arbitrarily large distances. Epsilon equals 1/2 v infinity squared. So the higher the hyperbolic excess velocity, the more energy the orbit has, and the higher the eccentricity. And 3 seats, Atlas, its orbital eccentricity, calculated from precise observations of its position and velocity, is approximately 6.139 plus or minus 0.00003. Let that number settle into your mind for a moment. 6.139, not 1.01, which would barely exceed parabolic, not 1.5, which would indicate moderate excess velocity. 6.139. This is the highest eccentricity ever measured for any object observed passing through our solar system. It exceeds the eccentricity of 1 Ioi Oumuamua, the first confirmed interstellar object, which had an eccentricity of approximately 1.2. It exceeds that of Tuzak Borisov, the second interstellar visitor, which had an eccentricity of approximately 3.4. 3I Atlas nearly doubles the eccentricity record, carrying with it implications of extraordinary velocity and ancient origins. An eccentricity of 6.139 means that 3C Atlas has tremendous excess energy. We can calculate its hyperbolic excess velocity, the speed it possessed when infinitely far from the Sun. For a hyperbolic orbit, the relationship between eccentricity and hyperbolic excess velocity is E equals square root of 1 plus 2 times V's infinity squared times A divided by mu, where A is the semi-major axis of the hyperbola. For hyperbolic orbits, the semi-major axis is negative by convention, and its magnitude relates to the energy. From the Viviva equation, we know V infinity equals square root of negative mu divided by A. We can work backward from the eccentricity. For 3I Atlas, with its enormous eccentricity of 6.139, the calculations indicate a hyperbolic excess velocity of approximately 18 kilometers per second. This means that even infinitely far from the Sun, where the Sun's gravity has essentially no effect, 3I Atlas would still be moving at 18 kilometers per second. This is the speed it brought with it from interstellar space, and the speed it will carry back out into interstellar space. This extraordinary eccentricity tells us that 3I Atlas is moving through our solar system with tremendous surplus energy. It came from interstellar space, already traveling fast, and our Sun's gravity did relatively little to its overall trajectory. The Sun bent the comet's path, certainly, causing it to curve as it passed through the inner solar system. But from the comet's perspective, the encounter was barely a deflection, a small perturbation in an otherwise nearly straight-line journey across the galaxy. The mathematics allows us to calculate precisely how much the Sun bent this trajectory. For a hyperbola, the angle between the incoming asymptote and the outgoing asymptote is related to the eccentricity by delta equals 2 times arctangent of 1 divided by square root of a squared minus 1. For 3E Atlas, with I equals 6.139, E squared equals 37.6892, 1E squared minus 1 equals 36.6892, 1 square root of 36.68921 equals approximately 6.05721, divided by 6.0572 equals an approximately 0.1651. Arctangent of 0.1651 equals an approximately 0.1636 radians, or 9.37 degrees delta equals 2 times 9.37 degrees equals approximately 18.74 degrees. So the Sun deflected 3 Stotes Atlas's path by less than 19 degrees. Imagine traveling for billions of years in essentially a straight line through the galaxy, then passing near a star, being deflected by less than 20 degrees, and continuing onward into the cosmic void. From the comet's perspective, from the viewpoint of an object that has crossed thousands of light years of space, the sun is barely a bump in the road, a minor gravitational obstacle that momentarily curved its ancient path. The trajectory is also notably well aligned with the ecliptic plane, the flat disk in which our planets orbit the sun. The comet's orbital inclination is listed as 175 degrees. In orbital mechanics, inclinations are measured from 0 to 180 degrees. An inclination of 0 degrees means the orbit is in the same plane as the ecliptic, moving in the same direction as the planets, prograde. An inclination of 90 degrees means the orbit is perpendicular to the ecliptic, moving over the poles. An inclination of 180 degrees means the orbit is in the ecliptic plane, but moving opposite to the planets, retrograde. 3i Atlas's inclination of 175 degrees means it's moving retrograde, opposite to the planetary direction, but tilted only 5 degrees from the ecliptic plane. This is somewhat unusual. Interstellar objects can approach from any direction in three-dimensional space. And the fact that 3i Atlas arrived so closely aligned with our planetary disk is largely a matter of chance, a random arrangement of angles. But it's a fortunate chance for astronomers, because objects moving roughly in the ecliptic plane are easier to track and observe from Earth-based telescopes. This alignment also affected the discovery timing. Objects that cross the ecliptic plane spend more time against the rich star fields of the Milky Way, making them harder to detect. Objects that move far above or below the ecliptic plane spend more time against sparser fields of distant galaxies, making them easier to spot. 3i Atlas's near-ecliptic trajectory meant it passed through dense stellar regions, likely delaying its discovery. But once found, once tracked, once its orbit was calculated with precision, the mathematics spoke with absolute clarity. This was no ordinary comet. This was a visitor from another world, from another stellar system, from another era of the galaxy's history. The eccentricity of 6.139 was the number that made this truth irrefutable, the mathematical signature that could not be explained away or reinterpreted. In the language of orbital mechanics, in the precise equations that describe how objects move under gravity's influence, 3i Atlas proclaimed its origin. I come from beyond. Now that we understand the mathematics that identifies 3i Atlas as interstellar, let us trace its journey through our solar system and calculate the numbers that describe its brief visitation. The comet reached its closest approach to the Sun on October the 29th, 2025, at precisely 11 hours and 36 minutes Universal Time. At this moment of perihelion, 3i Atlas was 1.36 astronomical units from our star. Let's pause here and understand what an astronomical unit means, for it is the fundamental ruler we use to measure the architecture of our solar system. 1 astronomical unit, abbreviated AU, is defined as exactly 149,597,870,700 meters. In more familiar terms, that's approximately 150 million kilometers, or 93 million miles. This is the average distance from Earth to the Sun, light traveling at its constant speed of 299,792 kilometers per second. takes about 8 minutes and 20 seconds to cross 1 astronomical unit. When you see sunlight, you're seeing the sun as it was 8 minutes ago. The light left our star, crossed the void of space at the ultimate cosmic speed limit, and arrived at your eyes after journeying for 500 seconds. So when we say that 3I Atlas reached perihelion at 1.36 AU, we mean it came within 203 million kilometers, or 126 million miles, of the Sun. That's closer than Mars typically orbits, but farther than Earth. At this distance, and when traveling at its maximum velocity of 68 kilometers per second relative to the Sun, 3A Atlas swept past our star in an elegant arc. The mathematics of its hyperbolic trajectory meant that it approached, reached perihelion, and began its departure all in one continuous, never-repeating motion. We can calculate the angle of deflection using the relationship between eccentricity and the asymptotic angle. For a hyperbola, the angle between the incoming and outgoing asymptotes is given by 2 times the arctangent of 1 divided by the square root of e squared minus 1. For 3I Atlas, with its eccentricity of 6.139, this works out to approximately 18.9 degrees. The Sun bent its path by less than 19 degrees. Imagine traveling billions of years in essentially a straight line, then passing near a star, being deflected by less than 20 degrees, and continuing onward. The star, from the comet's perspective, is barely a perturbation in its ancient journey. The comet's trajectory is also remarkably well aligned with the ecliptic plane, the flat disk in which our planets orbit. Its orbital inclination is 175 degrees, which in the language of orbital mechanics means it's traveling retrograde, moving opposite to the direction the planets orbit, but with only a 5-degree tilt relative to the planetary plane. This is somewhat unusual. Interstellar objects approach our solar system from random directions. The fact that 3I Atlas arrived so closely aligned with our planetary disk is a coincidence, a random arrangement of angles that made it easier to discover and observe. The ancient journey measured in billions. Now we come to perhaps the most profound mathematical question. How long has 3I Atlas been traveling through space? The answer requires us to think about the motion of stars through our galaxy and the typical velocities of objects ejected from stellar systems. When 3I Atlas arrived at our solar system, scientists analyzed its velocity components in the galactic coordinate system. This is a 3-dimensional framework centered on the galaxy itself, with directions defined relative to the galactic center and the galactic plane. The comet was moving away from the galactic center with a radial velocity component of negative 51 kilometers per second relative to the Sun. It was also moving upward through the galactic plane with a vertical velocity component of positive 18.5 kilometers per second. This vertical velocity is particularly telling. Most stars in the thin disk of the Milky Way, where our Sun resides, have vertical velocities of only a few kilometers per second. They orbit the galactic center in relatively flat, circular paths. But 3I Atlas has a much higher vertical velocity, suggesting it follows a tilted orbit around the galaxy. Based on these velocity components and the typical characteristics of different stellar populations in the Milky Way, astronomers can estimate the age of 3I Atlas. A study published in July 2025 estimated with 68% confidence that the comet is between 7.6 and 14 billion years old. Let those numbers rest gently in your mind. 7.6 to 14 billion years. Our solar system, our Earth, our Sun, formed approximately 4.6 billion years ago. If 3I Atlas is on the older end of that estimate, it is 3 times as old as everything we know. It predates our world. It predates our star. It has been traveling through the galaxy since before the sun even existed. To understand what this means, let's do some gentle mathematics. The Milky Way galaxy rotates. Our sun orbits the galactic center at approximately 220 kilometers per second, taking about 225 to 250 million years to complete one orbit. This vast cycle is sometimes called a galactic year. In the entire history of Earth, from its formation to now, our planet has completed approximately 20 orbits around the galaxy. 20 times around, 20 galactic years. If 3I Atlas is 14 billion years old, and we use a galactic year of 230 million years, then this comet has completed approximately 61 orbits around the Milky Way. 61 times around. But here's where the mathematics becomes even more profound. 3I Atlas doesn't orbit in the flat disk like the Sun does. Its high vertical velocity means its path weaves above and below the galactic plane, like a wave oscillating through the Milky Way's structure. The time it takes to complete one full oscillation through the galactic plane depends on the gravitational field of the galaxy, but for typical thick disk orbits, this period is on the order of 100 million years. Over 14 billion years, 3I Atlas might have bobbed up and down through the galaxy's disk 140 times. 140 crossings through the starlit plane of our galaxy. Each crossing taking it through regions dense with molecular clouds, through spiral arms bright with newborn stars, through the quieter spaces between. Let us calculate some of the distances involved in 3I Atlas's journey, translating cosmic numbers into forms we can contemplate as we rest. The comet's velocity relative to the local standard of rest in our galaxy, accounting for all 3 components of motion, is approximately 62 kilometers per second. This is the speed at which it moves through the general galactic neighborhood when we subtract out the sun's own peculiar motion. At 62 kilometers per second, how far does 3I Atlas travel in various intervals of time? In 1 second, 62 kilometers, about 38 miles, the distance from one city to another. In 1 minute, 3,720 kilometers, the distance across a small continent. In 1 hour, 223,200 kilometers, more than halfway to the moon. In 1 day, 5,356,800 kilometers, 14 times the distance from Earth to the moon. In 1 year, approximately 1.96 billion kilometers. This is 13 astronomical units, enough to cross from the Sun to Saturn's orbit. Over 1 million years, it travels 1.96 trillion kilometers. Over 1 billion years, 1.96 quadrillion kilometers. That's about 207 light years. If 3I Atlas has been traveling for 10 billion years at this velocity, it has covered approximately 2,070 light years. But this calculation is simplified. The comet's velocity hasn't been constant. It has passed near other stars, been deflected by their gravity. It has moved through different regions of the galaxy where gravitational fields vary. It may have been accelerated during its ejection from its home system. Still, these numbers give us a sense of scale. Even if the comet has covered only 1,000 light years in 10 billion years, it has traversed distances that dwarf our entire neighborhood of stars. The nearest star to our Sun, Proxima Centauri, is 4.24 light years away. The comet's journey, measured in light years, could have taken it past thousands of stellar systems through dozens of spiral arms across vast stretches of near-empty space. Let's explore the velocity of 3I Atlas in greater depth, comparing it to other known velocities in the universe to understand just how fast this ancient wanderer moves. We've established that at perihelion, 3I Atlas was moving at 68 kilometers per second relative to the Sun. That's 244,800 kilometers per hour, or 152,160 miles per hour. To put this in perspective, imagine if you could travel at this speed on Earth. You could circumnavigate the globe in just over 1 minute and 36 seconds. The Earth's equator is about 40,075 kilometers around, and at 68 kilometers per second, you'd complete a full lap in 589 seconds. You could travel from New York to London in about 163 seconds, or just under 3 minutes. The distance of approximately 5,575 kilometers would pass beneath you in the time it takes to brew a pot of tea. But in the context of the solar system, this velocity, while impressive, is not unique. Earth itself orbits the Sun at approximately 29.78 kilometers per second. Venus moves at 35.02 kilometers per second. Mercury, closest to the Sun, screams through its orbit at 47.36 kilometers per second. The difference is that these planets are in closed orbits. Their velocities are just right to maintain stable ellipses around the Sun. 3I Atlas's velocity exceeds escape velocity by a comfortable margin. It's not orbiting, it's escaping. At Earth's orbital distance, the escape velocity from the Sun is approximately 42.1 kilometers per second. 3I Atlas, even far from perihelion, moves faster than this. Even when it was first discovered, still 670 million kilometers from the Sun, it was traveling at approximately 61.4 kilometers per second, well above the local escape velocity. Now let's compare this to other types of high-velocity objects in our galaxy. Most stars in the galactic disk move at velocities between 100 and 200 kilometers per second relative to the galactic center. Our Sun moves at approximately 220 kilometers per second in its orbit around the Milky Way. Some stars, called high-velocity stars, move much faster. Objects with velocities exceeding 65 to 100 kilometers per second relative to the local stellar neighborhood are considered high-velocity stars. Even rarer are hypervelocity stars, which move fast enough to escape the Milky Way's gravity entirely. The escape velocity from the galaxy at our solar system's location is approximately 537 kilometers per second. Some hypervelocity stars near the galactic center have been observed moving at close to 1,000 kilometers per second. 3I Atlas, with its galactic velocity of about 62 kilometers per second relative to the local standard of rest, is not a hypervelocity object. It's bound to the galaxy. It will continue orbiting the Milky Way, moving in its tilted path, weaving through the galactic structure for billions of years to come. But within the context of objects visiting our solar system, its velocity is extraordinary. It's moving fast enough to have traveled vast distances over cosmic time, fast enough to pass through solar systems in mere decades rather than centuries, fast enough to make our sun's gravitational pull merely a gentle suggestion rather than a binding constraint. Let's calculate some of the specific details of 3I Atlas's perihelion passage, the moment when it reached its closest approach to our Sun. At perihelion, on October the 29th, 2025, the comet was at 1.36 astronomical units from the Sun. Let's express this distance in different units to appreciate its scale. 1.36 AU equals approximately 203,392,674 kilometers. In miles, that's about 126,385,500 miles. In light travel time, this distance is approximately 11 minutes and 18 seconds. A photon of light leaving the Sun would reach the comet's position at perihelion after traveling for 678 seconds. The comet's speed at perihelion was 68 kilometers per second. We can calculate how long it took to traverse various distances around perihelion. The Sun's diameter is approximately 1,391,000 kilometers. At 68 kilometers per second, 3I or Atlas would cross a distance equal to the Sun's diameter in about 5 hours and 45 minutes, or 20,454 seconds. From a distance of 1.36 AU, the Sun would appear to 3I Atlas at an angular diameter of approximately 0.4 degrees, similar to how the Sun appears from Earth, but slightly smaller. Our eyes see the Sun at about 0.53 degrees across, so from the comet's perspective at perihelion, the Sun would appear about 75% as large. The gravitational force experienced by 3I's Atlas at perihelion can be calculated using Newton's law of universal gravitation. F equals G times m times m divided by r squared, where G is the gravitational constant, m is the mass of the Sun, m is the mass of the comet, and r is the distance between them. The Sun's mass is approximately 1.989 times 10 to the power of 30 kilograms. The gravitational parameter of the Sun, which is G times m, equals about 1.327 times 10 to the power of 20 cubic meters per second squared. If we estimate the comet's mass at around 10 to the power of 14 kilograms, a reasonable guess for a nucleus a few kilometers across, then at perihelion, the gravitational force would be approximately 8.28 times 10 to the power of 8 newtons. That's 828 million newtons, a tremendous force. But spread across the comet's mass, this produces an acceleration of about 8.28 times 10 to the negative 6 meters per second squared. This is approximately 1/800,000th of the gravitational acceleration we experience on Earth's surface. This tiny acceleration, acting over the days and weeks the comet spent near perihelion, was enough to bend its trajectory by those 19 degrees we calculated earlier, enough to curve its path from one straight line asymptote to another, but not enough to capture it, not enough to bind it. While 3I Atlas came relatively close to the Sun by interstellar standards, it never came particularly near to Earth. Let's calculate the distances involved. At perihelion, when the comet was closest to the Sun, Earth was on the opposite side of the Sun from the comet's position. This is simply a matter of timing, of where Earth happened to be in its orbit on October 29th. The comet's closest approach to Earth occurred on December 19th, 2025, when it passed at approximately 1.8 astronomical units from our planet. 1.8 AU equals approximately 269,276,167 kilometers, or 167,340,000 miles. For comparison, Mars at its closest approach to Earth comes within about 56 million kilometers. Venus at its closest approaches to within about 40 million kilometers. So 3I Atlas, even at its nearest, was about 5 times farther from Earth than Venus ever gets. From our planet, the comet appeared as a faint smudge, requiring telescopes to observe. At this closest approach distance, light from Earth would take about 14 minutes and 59 seconds to reach the comet. If you sent a radio signal to 3I Atlas on December 19th, and if it could send a signal back instantly, you would receive a reply after about 29 minutes and 58 seconds. The comet's angular motion across Earth's sky was measurable but slow. From December to January, as it receded from our planet, it moved through the constellations Virgo and Leo, its brightness gradually diminishing. Astronomers estimated its brightness at closest approach to be around apparent magnitude 12. For reference, the human eye can see down to about magnitude 6 under perfect dark sky conditions. Magnitude 12 is approximately 40 times fainter than the faintest stars visible to the naked eye, requiring binoculars or telescopes to observe. To fully appreciate 3I Atlas's journey, we need to understand the nature of the space through which it has traveled for billions of years. Interstellar space, the vast regions between the stars, is not empty. It contains the interstellar medium, a thin soup of gas and dust with an average density of about 1 atom per cubic centimeter. This seems extraordinarily sparse. For comparison, the air you breathe contains about 2.5 times 10 to the power of 19 molecules per cubic centimeter. The interstellar medium is about 10 to the power of 19 times less dense than Earth's atmosphere. Yet over the vast distances of interstellar space, even this tenuous material accumulates. A cubic light year of space, a volume that's 9.46 times 10 to the power of 15 meters on each side, contains enormous amounts of matter when you add it all up. The volume of a cube with sides of 1 light year is approximately 8.47 times 10 to the power of 47 cubic meters. At 1 atom per cubic centimeter, which is 10 to the power of 6 cubic centimeters per cubic meter, times 10 to the power of negative 6 atoms per cubic centimeter, we get approximately 8.47 times 10 to the power of 53 atoms in a cubic light year. Most of these atoms are hydrogen with some helium. The mass of a hydrogen atom is about 1.67 times 10 to the power of negative 27 kilograms. So a cubic light year of interstellar medium contains approximately 1.4 times 10 to the power of 27 kilograms of matter, or about 700,000 times the mass of Earth. As 3I Atlas travels through this medium at 62 kilometers per second, it encounters resistance. Particles of interstellar gas collide with the comet, transferring momentum. Over billions of years, this drag force has a measurable effect. The drag force can be estimated using F equals 1/2 times r osus times vi squared times c times a, where rho is the density of the medium, v is the velocity, c is the drag coefficient, and a is the cross-sectional area. For interstellar space, with a density of about 1.67 times 10 to the power of negative 21 kilograms per cubic meter, and assuming a comet with a cross-sectional area of perhaps 10 square kilometers, or 10 to the power of 7 square meters, and a drag coefficient around 1, we get F equals approximately 1/2 times 1.67 times 10 to the negative 21 times 62 squared times 1 times 10 to the power of 7. This equals about 3.2 times 10 to the negative 9 newtons. This is an extraordinarily tiny force, about the weight of a small grain of sand on Earth. But acting continuously over billions of years, it accumulates. The work done by this drag force over a distance of 1,000 light years, which is about 9.46 times 10 to the power of 18 meters, equals W equals F times D equals 3.2 times 10 to the negative 9 times 9.46 times 10 to the power of 18. This equals approximately 3 times 10 to the power of 10 joules, or 30 billion joules. For comparison, the kinetic energy of 3I Atlas, moving at 62 kilometers per second, with an estimated mass of 10 to the power of 14 kilograms, is approximately 1.9 times 10 to the power of 20 joules. The drag force over 1,000 light years would reduce the comet's kinetic energy by about 1 part in 6 billion, essentially negligible. The comet's velocity has remained virtually unchanged over its entire journey through the galaxy. The mathematics and observations suggest that 3I Atlas formed in the earliest days of another stellar system, possibly billions of years before our own sun existed. When stars form, they coalesce from collapsing clouds of gas and dust. These clouds, typically a few light years across, contain enough material to form not just the star, but an entire planetary system. As the cloud collapses under gravity, it flattens into a disk due to conservation of angular momentum. The equations governing this process are elegant. L equals R cross V times m angular momentum. L is conserved, so as the radius r decreases, the velocity v must increase, causing the disk to spin faster as it contracts. Within this protoplanetary disk, small particles collide and stick together through processes we're still working to understand fully. Dust grains, measuring micrometers across, grow into pebbles, then into planetesimals kilometers in size. These planetesimals are the building blocks of planets. In the inner regions of the disk, where temperatures are higher, they form from rock and metal. In the outer regions, beyond what's called the frost line, temperatures are low enough for water and other volatiles to freeze. Here, planetesimals incorporate vast amounts of ice. 3I Atlas, based on its observed activity when heated by our sun, is rich in volatile ices. This suggests it formed in the outer regions of its birth system, beyond its home star's frost line. The age estimates of 7.6 to 14 billion years place its formation during an era when our galaxy was younger, when stars had less heavy elements in their composition. The earliest generations of stars formed from nearly pure hydrogen and helium. Subsequent generations incorporated elements forged in the cores of earlier stars and scattered by supernova explosions. The vertical velocity component of 3I Atlas suggests it came from the thick disk or thin disk population of the Milky Way, regions containing stars that are old but not the absolute oldest. The comet likely formed around a star that lived, evolved, and possibly died billions of years ago. How was it ejected from its home system? The mathematics of planetary dynamics offers several scenarios. The most common mechanism involves gravitational interactions with giant planets. As planets form and migrate through their birth disk, they scatter smaller objects. Some are scattered inward, some outward. Those scattered outward with sufficient velocity escape the stellar system entirely. The escape velocity from a solar-type star at a distance of, say, 50 AU, similar to the Kuiper belt in our solar system, is about 6.6 kilometers per second. If a planetesimal encounters a Jupiter-sized planet and receives a gravitational kick, it can easily exceed this velocity. Once ejected, the planetesimal becomes an interstellar wanderer. Its velocity relative to its home star might be only a few kilometers per second, but combined with the star's own motion through the galaxy, it joins the general population of stars orbiting the galactic center. Throughout its passage through our solar system, 3I Atlas was observed by an unprecedented number of scientific instruments, each adding pieces to the mathematical puzzle of its nature and origin. NASA coordinated observations from 12 different spacecraft and space telescopes, along with ground-based observatories worldwide. This multi-instrument campaign allowed astronomers to study the comet from different angles, at different wavelengths, and at different distances. The Mars Reconnaissance Orbiter observed the comet from a distance of about 30 million kilometers on October 2nd, 2025, just one day before the comet made its closest approach to Mars at about 29 million kilometers. When the MAVEN spacecraft at Mars used its ultraviolet spectrograph to image the hydrogen atoms surrounding the comet, revealing the coma's extent and composition. These observations showed hydrogen emission extending in a diffuse halo around the nucleus, evidence of water molecules being broken apart by solar ultraviolet radiation. The James Webb Space Telescope observed 3I Atlas with its near-infrared spectrograph, analyzing the composition of the gases being released. These observations revealed that the comet was releasing more carbon dioxide than water, an unusual ratio compared to typical solar system comets. The ratio of carbon dioxide to water can be expressed mathematically. For most comets from our solar system's Oort cloud, the ratio of CO2 to H2O molecules is typically between 0.01 and 0.1. For 3I Atlas, this ratio appeared to be greater than 1, meaning more carbon dioxide than water. This compositional difference might reflect the conditions in the comet's birth system. Different stellar systems have different frost line locations, different temperature gradients, different abundances of various molecules. 3I Atlas carries the chemical fingerprint of another place, another time. The Hubble Space Telescope captured images showing a faint coma and hints of a tail, structures formed as sunlight heats the nucleus and releases gases and dust. By analyzing the brightness and size of the coma, Astronomers estimated the nucleus size to be somewhere between a few hundred meters and a few kilometers across. Let's calculate the mass based on different size estimates. If the nucleus is 1 kilometer in diameter, a sphere with a radius of 500 meters, its volume is V equals 4/3 pi AR cubed equals 4/3 pi times 500 cubed equals approximately 5.24 times 10 to the power of 8 cubic meters, assuming a density similar to other comets, about 500 kilograms per cubic meter. The mass would be m equals rho times thus equals 500 times 5.24 times 10 to the power of 8 equals approximately 2.6 times 10 to the power of 11 kilograms. If the nucleus is 5 kilometers in diameter with a radius of 2,500 meters, V equals 4/3 pi times 2,500 cubed equals approximately 6.55 times 10 to the power of 10 cubic meters. Mass equals 500 times 6.55 times 10 to the power of 10 equals approximately 3.27 times 10 to the power of 13 kilograms. These estimates span 2 orders of magnitude, reflecting our uncertainty. The comet is too far away, too faint, for its nucleus to be resolved directly by our telescopes. But regardless of exact mass, we can calculate its kinetic energy. Even with the lower mass estimate of 2.6 times 10 to the power of 11 kilograms, moving at 62 kilometers per second, Ke equals 1/2 mv squared equals 1/2 times 2.6 times 10 to the power of 11 times 62,000 squared. This equals approximately 5 times 10 to the power of 20 joules. For comparison, the asteroid impact that killed the dinosaurs released an estimated 4.2 times 10 to the power of 23 joules. 3I Atlas, despite its tremendous velocity, carries far less energy simply because its mass is smaller. Now let's trace 3I Atlas's path into the future and calculate where it will be in the years and centuries to come. After passing perihelion on October 29th, 2025, the comet began its outbound journey, moving away from the Sun at gradually decreasing speed as the Sun's gravity continued to tug at it. By late November and through December, it was observable from Earth's northern hemisphere in the pre-dawn sky, moving through the constellation Virgo. Its brightness, which had peaked near magnitude 12 at closest approach to Earth, began to fade as it receded. Let's calculate its position at various future dates. On January 1st, 2026, the comet will be approximately 2.15 AU from the Sun and about 2.8 AU from Earth. At this distance, light from the Sun takes about 17 minutes and 51 seconds to reach the comet. On July 1st, 2026, it will be approximately 3.3 AU from the Sun, traveling at about 49 kilometers per second relative to our star. On January 1st, 2027, it will be approximately 4.5 AU from the Sun, about the distance of Jupiter's orbit, moving at approximately 41 kilometers per second. As the comet continues outward, it will cross the orbit of Saturn around 2028, the orbit of Uranus around 2032, and the orbit of Neptune around 2037. By the time it reaches the heliopause, the boundary where the Sun's solar wind gives way to interstellar space, approximately 120 AU from the Sun, it will be around 2085. At this point, 6 decades from its perihelion passage, it will be moving at approximately 21 kilometers per second relative to the Sun, still carrying significant excess velocity. Beyond the heliopause lies the Oort cloud, a theoretical spherical shell of icy bodies extending from about 2,000 to 100,000 AU from the Sun. 3I Atlas will pass through this region over the next several thousand years. At 1,000 AU, reached around the year 4000, it will be moving at approximately 18.9 kilometers per second relative to the Sun. At 10,000 AU, reached around the year 34,000, it will be moving at approximately 18.2 kilometers per second. At 100,000 AU, at the outer edge of the Sun's gravitational influence, reached around the year 330,000, it will be moving at approximately 18 kilometers per second, its velocity having asymptotically approached this value. This asymptotic velocity, 18 kilometers per second relative to the Sun, represents the hyperbolic excess velocity, the speed at which the comet entered our solar system and the speed at which it will leave. Combined with the Sun's own motion through the galaxy, 3I Atlas will continue its journey through the Milky Way, its path through our solar system merely a brief perturbation in billions of years of travel. As we contemplate the numbers we've explored tonight, patterns emerge. The mathematics of 3I Atlas tells a story written in equations, expressed in velocities and distances and timescales. An eccentricity of 6.139, a velocity of 68 kilometers per second at perihelion, an age of 7 to 14 billion years, a distance traveled over cosmic time measured in thousands of light years. Each number is a window into processes that dwarf human timescales, that stretch beyond our everyday comprehension. Yet mathematics makes them accessible through equations, through calculations, through the patient application of physical laws. We can trace the path of this ancient wanderer. We can calculate that it has orbited the galaxy perhaps 61 times. We can estimate that it has covered distances that would span thousands of stellar systems. We can predict where it will be centuries and millennia from now, using the same equations that describe the falling of an apple or the orbit of the moon. This is the power of mathematics. It connects the smallest scales to the largest. The same gravitational constant g appears in the equation for a ball falling on Earth and in the equation describing 3I Atlas's path through our solar system. The same principles of energy and momentum conservation that govern your car's motion govern a comet's journey across light years. When we look at 3I Atlas through the lens of mathematics, we see not just a visitor from another stellar system, but a testament to the deep patterns underlying reality. The hyperbolic trajectory it follows is not arbitrary. It emerges necessarily from the interplay of velocity and gravity, from the fundamental equation of motion. The time it has traveled, while vast by human standards, is finite and calculable. The distance it will travel in the future is predictable. The energy it carries is conserved, transforming from kinetic to potential and back again, but never created or destroyed. Before we bring our journey tonight to a close, let's consider one more set of calculations. Numbers that connect the mathematics of 3I Atlas to our own experience. The atoms that make up the comet, forged in stars that lived and died billions of years ago, are the same types of atoms that compose your body: carbon, oxygen, nitrogen, silicon, iron. The comet carries perhaps 10 to the power of 38 atoms, give or take a few orders of magnitude. Your body contains approximately 7 times 10 to the power of 27 atoms. The comet, even if relatively small, contains 10 billion times as many atoms as you do. Each of those atoms has a story written in quantum mechanics, in the fusion reactions of ancient stars, in the chemistry of molecular clouds and protoplanetary disks. The mathematics that describes electron orbitals, that predicts chemical reactions, that governs the formation of ice crystals in the cold outer regions of a stellar system, connects your existence to this interstellar visitor. The photons that bounced off 3I Atlas and entered our telescopes traveled at the speed of light, covering the distance in minutes to hours depending on the comet's position. Those same electromagnetic equations that describe light from the comet also describe the light entering your eyes right now, if you're reading these words in the gentle darkness before sleep. The gravitational force that bent the comet's path past the sun is the same force that keeps you grounded on Earth, that makes your heart pump blood throughout your body, that shapes galaxies over billions of years. Mathematics reveals these connections. It shows us that we are not separate from the cosmos, but part of it. The same laws apply everywhere, at all scales, at all times. And now, as the numbers begin to drift, like stars across the darkness behind your thoughts, we come to the end of our exploration. We've traced the path of 3I Atlas through equations and calculations, through orbital mechanics and galactic dynamics. We've followed it across billions of years, across thousands of light years, through 61 orbits around the Milky Way. We've measured its velocity in kilometers per second and miles per hour. We've calculated its kinetic energy in joules, its orbital eccentricity as a dimensionless number that speaks volumes. We've estimated its age in billions of years, its size in kilometers, its mass in kilograms. All of these numbers tell a story of formation in the dawn of another stellar system, of ejection into the vast spaces between stars, of a journey measured in cosmic time through the cold near vacuum of interstellar space, past other stars whose light never warmed this ancient wanderer. And then, by chance, by the random geometry of galactic orbits, its path intersected ours. For a few months in 2025, we shared our sky with this visitor. Our telescopes captured its light. Our spacecraft observed its passage. Our calculations traced its trajectory. The mathematics we used to understand 3I Atlas is the same mathematics humans have been developing for centuries. From Kepler's laws of orbital motion to Newton's law of universal gravitation, from the vis viva equation to the hyperbolic trajectory formulas, each piece of mathematical knowledge added another tool for understanding. Tonight, as you rest, that comet continues its journey. Right now, at this very moment, it's moving farther from the sun at approximately 51 kilometers per second. With each second, it travels 51,000 meters farther from our star. With each minute, it travels 3,060 kilometers. With each hour, 183,600 kilometers. By the time you wake tomorrow, it will be nearly 4.4 million kilometers farther away than it is right now. By next week, it will have traveled 30.5 million kilometers. By next month, 130.8 million kilometers. And it will never return. This is its one and only visit to our corner of the galaxy. Our solar system was a waypoint, a brief curve in its path, a temporary warming by our sun before the return to the cold of interstellar space. But through mathematics, we've captured its passage. We've measured, some calculated, understood. We've taken something vast and ancient and made it comprehensible through numbers. If this journey through the mathematics of 3i Atlas has helped you find peace tonight, if it's given you gentle thoughts to ease you into sleep, please consider liking and subscribing to the channel. These explorations continue, each one a different corner of the mathematical universe, each one designed to bring wonder and rest in equal measure. Sleep well tonight, knowing that above you, beyond the clouds and the atmosphere, beyond the moon and the planets, an ancient wanderer continues its journey, its path governed by equations we can write, its future predictable through calculations we can perform, its story written in the language of mathematics that connects all things. The numbers will be here tomorrow. The comet will be farther away, but still calculable. The mathematics will remain, eternal and patient, waiting to reveal the next set of cosmic connections. Rest now. Let the equations drift away like stars fading into dawn. Let the numbers settle like dust particles finding their place in space. Let the mathematics of this ancient journey carry you gently into dreams. Good night.